uh, as we mentioned before, we showed three different types of formulas for the derivative: forward, backward, and central divided difference. And we showed that the central has a big advantage over the forward and the backward, as it converge much faster, and the rate of reduction in the error is in the order of delta x squared. However, these three formulas are considered the basic formulas that we use them to find the derivative in a numerical way, but they are not the only formulas. There are many other formulas, and in this question we want to show you, or we need to show that the derivative also could be given by this formula, and this formula will give us order of an error which is equal to h squared or delta x squared. Just for your information here, that delta x that we used before is equal to h in this question. It's the same thing. It's just a symbolic that's used by box. Some people they use h, some people use delta x, but they are both the same. So we want to show that this formula first is correct, and then that the order of the error is h squared. And this is now we understand how important is this, because the order of the error will tell us the rate of convergence, how fast we will be converging, and it will tell us an idea about if I reduce the delta x by a half or by a quarter, how much will be the reduction in the error as well. So let's start without further ado. So we know before that f of x plus h, which we call it f of xi plus 1 in the previous. So we used this before, xi plus 1. This is exactly the same of f of x plus h. Exactly mean the same thing, means f of x plus delta x. So if you see using this or that, they all mean the same thing, which means that what is the function defined at a future data point that we don't know. That's what does it mean, okay? And we know that to apply the Taylor expansion, okay, that we have to have the function and all of its derivatives are defined at the function. Okay, so we know that this is now equal to f of x, which is the function at x, okay, plus h f prime of x plus h squared divided by 2 factorial f double prime of x plus h cube divided by 3 factorial f triple of x plus etc. So this is the definition of the Taylor expansion that we use. Okay, excellent. Now what I want to find, or I want to represent f prime of x, which is here, in terms of f of x, which is here, f of x plus of h, which is here, and f of x plus 2h. So I have to define this, which is my f of x plus 2h. So now this is like finding f of x of I plus 2, meaning that finding the function defined at 2 increments. So I will need to increase the x by 2 delta of x to find the function defined at x plus 2h. That's all. What does it mean? So basically what we will do, we have this formula. I will just substitute h with 2h. That's it, nothing else. So this becomes f of x plus 2 of h. So I'm just replacing h with 2 of h, f prime of x, plus same thing here. This becomes 2 of h squared divided by 2 factorial f prime of x plus 2h to the power of 3 3 factorial f, and so on and so forth. Okay, so let me simplify a little bit. So this becomes equal to f of x plus 2h f prime of x plus 4h squared divided by 2 factorial f double prime of x plus 8h cube divided by 3 factorial f triple prime of x, and so on and so forth. Okay. Now also I need not just f of x plus of h, but I need 4 times this. So I will multiply this with 4. So we need 4 times f of x plus h. So whenever you are asked a question like this to prove certain statement, this is the approach you should take. So I will multiply this with 4, all the terms. So this becomes 4 f of x plus 4h f prime of x plus 4h squared divided by 2 factorial f double prime of x plus 4h cube over 3 factorial f of x plus. Now what we have here, we have 4 of h minus f of x plus 2h. So I need to subtract these two together. Let's say I subtract this from this. So when I subtract this minus this, okay, so we have here f of x, we have here 4, so this becomes minus I don't know why the screen, let me just okay, so let me just the screen, I don't know why it becomes smaller like this. Okay. Okay. So I will subtract this minus this minus this minus this, and this minus this. So if we do that, what we will get, we will have f of x plus 2h minus 4 f of x plus h. Now, if I subtract these two equations together, we'll have minus 3f of x minus 2h f prime of x plus 4h cube divided by 3 factorial f triple of x, etc. Now, this is what I want in one side, so I will move this to this side. I will move this to the other side. So what we will have here, so I just move this one here, so it becomes 2h f prime of x will equal to minus 3 f of x plus 4f of x plus h minus f of x plus 2 of h, okay, minus 4, no, this is plus, because this is, I will just move this one here, this one this, so this is as it is. This is 4h cube over 3 factorial f, etc. Okay, now, okay, I have this now on one side, so I want to find f prime of x, so I will divide everything with 2 of h, so this becomes minus 3f of x plus 4 f of x plus h minus f of x plus 2 of h, all of this divided by 2 of h, plus I will divide 2 of h with this. Okay, so this will give me 2h squared divided by 3 factorial f of x, etc. So this is the formula, and the order of the error is h squared. Okay, so this is how we do this. This type of questions, a proof question. We'll try to find all the terms in the derivative, and then we keep only the smallest component of the error, because now we will have here other terms like h to the power 4, h to the power 5. This becomes sorry, this is the highest. This is the highest error, because remember, h is a small number, so h squared is higher than h to the power 4 is higher than h to the, so this is the highest order of the error. Anything else can be neglected with respect to this one, and this is in the literature is called a 3-point forward divided difference. Okay, so this is just one example. There are many other formulas that we can prove, they can be short, but this is the approach for that. Okay, now this we claim that this is an order of h squared. So if we just let me just do one thing here. Let me just insert a page here. And let me resolve the first example we had before using this formula. So now our f prime of x is equal to 3 f of x plus 4 of f of x plus delta x minus f of x minus 2 delta x. As you know, delta x and h is the same, divided by 2 delta of x. So I will use this to find the voltage at 10. This is the example. So it's 25 LDI by dt. This di by dt becomes, this is times minus 3I at 10 plus 4 of I at, this is x plus delta x. I remember 10 point, that was x, delta x was 0.5. So this is 10.5 minus I, this is plus through delta x, so this is minus I at 11. Okay, this is all of this divided by 2 times 0.5. Okay, now we come and substitute all these values in the formula that we have to find the I at 10, 10.5, and 11. And if you do all the substitution, you will find this is equal to 10.725 millivolt. Now, if I want to find the percentage error, so it is the actual value minus 10.725 divided by 11.35, 100%. And this gives me 5.5%. And so this is, if you recall, is closer, much closer to the CDD method. If you remember, the FDD and the BDD, the error was in the 20. Okay. Now, if you try to reduce this from 0.5 to 0.25, you will find that this error will be reduced by the order of h squared or delta x squared, or it will be like 1/4 of this error. Okay. Now, what if I want to find a higher order or derivative? Let's say, for example, I want to find the second derivative. So with the same approach, we need to actually derive this formula, okay? And we will derive it together. What is the derivation of the second derivative? What is it equal to? So as we know, f of x of I plus 1, I'm intentionally using different symbols so that you are used as I'm to the looking of the different symbols. So if you see different books, different notes, you will see that different people using different things. So it is, all of them are exactly the same. F of x of I plus 1, as I mentioned, it is f of x plus delta of x. So this is again from the Taylor expansion. Okay, so this is equal to f of x of I plus, this is the same, just the same formula we just had before, f prime of x of I delta of x plus f double prime of x of I divided by 2 factorial delta x squared plus f triple of x of I divided by 3 factorial delta x cube plus f 1, 2, 3, 4 x of I divided by 4 factorial delta x to the power of 4. Okay, and so on and so forth. Okay, and we can define f of x of I minus 1. So the only thing that we need to do, because we know that f of x of I plus 1 is equal to f of x I plus delta x. So x plus delta x, and f of x of I minus 1 will be f of x minus delta x. Okay, so the only thing I need to do here is to replace delta x with minus delta x, nothing else. Okay, so everything will be same except delta x's. I will change them to minus delta of x. So this becomes f of x of I minus f prime of x of I delta x plus, because this is delta x squared, f double prime of x of I divided by 2 factorial delta x squared minus f triple x of I delta x cube over 3 factorial plus f power 4th derivative x of I divided by 4 factorial delta x power of 4. Okay, so now we have this. I will do, I will just add this to this. So when you add these two terms together. Okay, and this will be cancelled with this. You add these two together, and this will be cancelled. So continue with this. If we have f of x of I plus 1 plus f of x of I minus 1, and this is equal to f of x of I plus f prime double prime of x of I delta x square plus f 1, 2, 3, 4 x of I delta x to the power 4 divided by 12, etc. Now I have here what I want in one side, so I will move everything else to the other side, and I will divide by delta x squared. So we have here f double prime of x of I, which is what I'm looking for, is equal to this f of x of I plus 1 plus or minus 2 f of x of I plus f of x of I minus 1. So this and this minus this, all of this divided by the delta x squared. So this is the formula. Now the error that we will have this. So this is delta of x 4 divided by delta x squared. So we will have delta of x squared. So the order of this will be delta of x squared. This is the order of the error. Okay. Before I move forward, there is one question here. It says, is there a general trick to do these proofs? Looks like this proof is a lot different than the previous one. Yes, it is different. The only thing I can tell you that all the proofs are around using or how to use the Taylor expansion. That's it. So once you know how to use the Taylor expansion, you understand it. All the proofs that we will be using is just using Taylor expansion, nothing else. So you just play with the terminologies, you subtract, you add until you get the formula that you are looking for. Nothing more, nothing less. Okay, so this is just a direct application. It says here, find the second derivative of the following function at x equal to 3 and delta x equal to 0.1. So here we want to find the second derivative. Now we know that the second derivative, if double prime of x equal to f of x plus delta x minus 2 f of x plus f of x minus delta of x divided by delta of x squared. Okay, so we have here x and delta x. This is the only thing I need to use in the formula, and we know x and we know delta x. Okay, so we need to find f double prime at 3. So I will just substitute here with these values. Okay, so this becomes f of 3 plus 0.1 minus 2 f at 3. Now f is 3.1. This is the function that I will be substitute plus f of 3 minus 0.1 divided by 0.1 squared. So now I will substitute in every all these values. So this will equal to 2 to the e of power 1.5 times x, which is 3.1 minus this. This is the function f of x. I will just substitute x with the value 3.1, 3, and 2.9. So minus 2 times 2, this becomes 4 e to the power of 1.5 times 3, and finally plus 2 e of the 1.5 times 2 by 0.01. If you do this, you will find that this is equal to 405.84. Okay. Now, if you come here and you do the second derivative of this, f prime of x will equal to 3 e to the 1.5 x. If double prime of x will come equal to 4.5 e to the 1.5 of x. Now, if double prime at 3, this is the exact, we'll get 405.08. So you see how close our approximation with the actual value. Okay. Let me see. There's another question. Can we use these equations right away, or are we expected to derive them first? No. These formulas have been already. I already gave the derivative to you. Okay. So there is no point to derive them again. And this is, as we know, all of us know that this is an open book exam. So if I ask you to derive this, you will just open the notes and you will copy it. So there is no point to ask you to do that. Okay. However, I might give you a different function, something not in the notes, and ask you to derive it. So the question will be to derive the formula. Okay, so that's a different story. Then you have to derive the formula. But if the question is to use, for example, CDD method, okay, then you go right away and use the formula that has been already derived for us. With this, we are done with the continuous function. Now, we will go for the discrete functions. And as a matter of fact, for you as an engineer, this is the more practical form that you need to use. Okay, as I mentioned before, for example, you are acquiring for example, in your car, you are acquiring your position continuously with delta t between one position to another. So if you take the derivative of this, you will be able to estimate your velocity. And sometimes you need to do that to estimate your velocity. Sometimes you need to estimate the velocity of the car in front of you. So if you can estimate their position using certain type of sensors, then you would be able to estimate their velocity. Why I need to estimate the velocity of the car in front of me? This is something extremely important if you are or if you are interested to work with autonomous cars. Autonomous cars, this is like a dream now. That start to become true nowadays. We start to have certain forms of autonomous car, but not the full scale of autonomous car where everything is 100% autonomous. So one of the things that you need to know is the velocity of the car around you, so that you don't exceed, you don't hit them, okay? And if there's something happened to them, you should be able to predict what is going on. Now, if you take the derivative of the velocities, you will get the acceleration, which is also very important. You want to know if the car is accelerating or decelerating, so that you will act accordingly to avoid any problems, any accidents in the highway or inside the city. So as a matter of fact, doing real-time derivative is extremely important. Now, there is also, for us as electrical engineers, if we are doing like continuous monitoring of a voltage or a current, and we have inductors, capacitors, and as we know, the relation between the current and the voltages in the capacitor and the inductor, either there's a derivative or there will be an integration. Okay, and we'll talk about integration, numerical integration next week. Okay, so you can find the voltage or the current of the inductor or the capacitor doing integration or derivative of the values of one to another, and this is something important. Sometimes we do that again in real time. So what you have points. You don't have a formula. You don't know what is the formula. You have a circuit. You are getting, let's say, a current that is discharging, or a voltage that is charging, and you want to find the other quantity. So you have points. You're measuring points. So you want to find the other one. So you need to take a derivative or integration. Okay. So it is why this is very important, and this is more practical than working with continuous functions. So whatever we do, or whatever we did in the previous section, when we dealt with continuous function, we will be dealing with it here, exactly the same thing. Now, I don't have a function, but I have rather points. Okay, so this 1 point, second, third, fourth, and between a point and the point, there is a delta of x. And we will see on Thursday that this is a limitation, because delta of x has to be constant. We cannot have delta of x that is varying, especially if you work with CDD, as we will see. Okay, so now if I want to define what is the derivative at point x, okay, so it will become f of x plus delta of x minus f of x. Okay, so you need to define the function at x plus delta of x, which is this function. So you need to define it here. So this will be your f of x plus delta x, and define it here, which is your f of x, and then you divide by your delta x. Now here the problem that you will face, that delta x you have no control. In the continuous function, we usually tell you, okay, start with delta x is equal to 0.5, reduce delta of x to 0.25, or delta x to 0.1. Whatever the value is, you can do that there, because you have a continuous function, and you can find this function at any value of delta of x that you want. However, here, no. Delta of x is something that you have no control. Delta of x is something fixed, because this is the time interval through which you will take your number. So when you set your system to acquire the data, you have to make sure that the delta of x that you want to use between one measurement to another is the value that you want, not less than that. Okay, so this is something very important. Now, same thing, this is for the FDD. We can do the same thing for the BDD. So this is f of x. We'll go backward here, and this is your f of x minus delta of x. Again, this is delta of x. Then we have the central. We take the two limits around x, and we divide by the summation of delta x plus delta of x. Okay, so let's have an example here. Okay, so here we have a data point x. Okay, this could be anything, could be time, could be a distance, so it doesn't really matter what is x. And it doesn't matter what is f of x. Again, this could be voltage, could be current, could be velocity, could be anything else. So there is no, we don't care about what is f of x. So we have three numbers, 3, 4, and 5. So this is my independent variables, and this is f of x. We have these three numbers, and we want to find f of prime at 4. And you can see here, I cannot say, for example, I cannot say I want to have f of prime at 3.5 because I don't have 3.5 here. Okay, so I cannot find it. This is cannot. So I'm limited in the options in discrete, and I'm keeping telling you this because I want to highlight the shortcomings that we have in the discrete, but we will find solutions to these problems, and I will discuss them on Thursday. So for this simple example, I want to find all the three different types of derivative: the forward, the backward, and the center. Okay, so I will come here. These are the numbers that I will have. So I will start with using the forward divided difference. Okay, so I want to find if 4, and this is, now we understand what does this mean. It is an approximation because there is an error. There is a truncation error we do here. We remove all higher orders from the tail because this is coming from the Taylor expansion. And we know that there are higher and higher orders. So now we understand this, and we understand why we said approximately. So this is f of 4. So to use the forward, I have to go this step. So I will have f of 5 minus f of 4 divided by the difference between them, which is 5 minus 4. So f of 5 is 125. F of 5. F of 4 is 64 divided by 1. And if you do this, this is equal to 61. If I use the backward BDD method, so your f prime of 4 approximately equal to now f of 4 minus f of 3 divided by 4 minus 3. So this is 64 minus 27 divided by 1, and this is equal to 37. And as we know that the CDD will give us always the average between this. So the f prime of 4 will equal to f of 5 minus f of 3 divided by 5 minus 3. And this equal to 125 minus 27 divided by 2, and this gives us 48 or 48. Yeah. Okay. Now, it's very important here to note that yes, I can calculate. Now, for example, can I calculate? Sorry. Can I calculate here? Can I calculate f prime of 5? Can I do that or not? Yes, I can. However, I can use only the BDD because I have a value. So this will be equal to f of 5 minus f of 4 divided by 5 minus 4. Okay, so I can do that, but this is only using the BDD. But I cannot use the FDD because I don't have 6. So I can find this using the BDD. In the same way, if I want to find f prime of 3, I can do that, f prime, using only the f of DD because I have this value and the value in front of it. So this becomes f of 4 minus f of 3 over 4 minus 3. But I cannot use, so this is only f DD. I cannot use the BDD. CDD here because I don't have the value at 2. Now, neither at 3 nor at 5 I can find the value of the derivative using CDD, because in CDD I have to have two values, a value on the front and a value on the back. Okay, so it's important to notice this. Let me see if there's any questions here. You mentioned we cannot calculate f prime of 3.5. I was thinking, can't we use CDD if 5 of 5, 4? Okay, now. Okay, this is a very, very good question. Let me answer the question. The question says, you mentioned we cannot find f prime of 3.5. I was thinking, can't we use CDD if f of 4 and of 3? So let me answer this question. Let me first clean this. Okay, let me just clean a little bit here to answer this question. So the question says that why we cannot, we have f of 3, we have f of 4, why we cannot find f of 3.5, which is, as I said, a good question. Okay, so let's look here. So what we want to have here, we want to find f of 3.5. So what will be f 3.5? If the central, this is the value that is here, f. Now the point is that because we don't know that we have to have the value defined at f 3.5. We don't know the value of 3.5. Okay. Now you are assuming that it becomes in between and it USS. Okay. So to be the maximum delta t I can have here is the delta t that I have in my measurement, which is 1. I don't have a measurement that's less than 1. So this is why this is undefined for me.